think I can get you all in one. Yeah.
Okay, so first of all, sorry for the delay. And camera is running?
Yeah.
Okay, great. Today I want to talk about representation of quantum states. We briefly talked about representation of pure states before. Now this is about arbitrary quantum states. So all density matrices and actually even more general quantum states, which you can't see in finite dimensions. They only exist in infinite dimensions. Will be treated within this framework, so it's very general. Before doing so, I quickly want to finish up what we did last time, just by saying something about this mapping from self-adjoint operators to arrows in our topos. So what we did last time, we defined mapping from self-adjoint operators in some phenomenon algebra into the arrows in our topos, which is set and op. These were arrows from sigma to some pre-sheaf R, which basically consists of intervals. And the idea was having unsharp values, which can, of course, become sharp in the sense that these intervals can shrink locally to a point. What I want to say about this is it's actually quite easy to see that delta is injective, so I can reconstruct a self-adjoint operator if I have given such an arrow. And this is actually quite simple. We had that, well, for all V, this component here was basically given by, what was it, the minimum in the self-adjoint operators of V, such that V is spectrally larger than A. Cheating a bit here because we had actually this approximation from above and we had another one from below. So this was the outer one, it was 1/2 of the story. It turns out actually 1/2 of the story is enough to reconstruct A. And it's very simple, you just have this for all V and take the minimum over all these components, delta O A, which you don't need this bracket here, V over all V, and this minimum is also in the spectral order. And since there is some Wheeler subalgebra V that contains A, it's very simple to see that this just becomes A, and all other operators are actually larger, all of the spectrum, and then because it's of course a partial modes in the usual linear order. So this is how you see injectivity. And the second thing is actually an open problem. First say that delta is not subjective. We would like that. We would like that all arrows from sigma to R come from operators, but that's not the case. You can construct counterexamples. So the open problem consists in characterizing which of these arrows come from self-adjoint operators, and I strongly suppose that we need, well, we have topology here, we have a distinguished family of sub-objects which behave like topology. We'll also need topology here, and then we can characterize continuous arrows in a certain way, and the ones we want will surely be continuous. In analogy to the ordinary Gelfand transform, if we look at this whole construction for an abelian algebra N, we basically get a Gelfand transformation here. There's still this thing that you have not just the abelian algebra, but also all its subalgebras, but that's not a major thing. So basically you get the ordinary Gelfand transform. This of course is a continuous function in the Gelfand spectrum, so the conjecture is that you will need something which is continuous in a suitable sense, and this has to be worked out. So currently this is not clear how to characterize arrows of form delta A, okay. That's actually all I wanted to say on this, and now I want to talk about representation of quantum states. So that's a very different story, obviously.
Andreas, can I just ask, what interpretation do you give the arrows which don't come from the self-adjoint operators?
Open problem.
They're not considered to be observables? Or?
They have. It's interesting. Currently, it's even open if they may have some physical interpretation. I don't know this. I don't claim this, but they are. Everything fits together nicely locally. So there are conditions because this is a natural transformation, such an arrow. So there are conditions, but these conditions are just local. They are between, well, they have V and you have a subalgebra, then of course the component at V of this natural transformation and the component V prime, they must all fit together nicely. But this is not strong enough to guarantee that globally it always comes from self-adjoint operator. But locally you wouldn't see this. So if you don't have a global perspective, you wouldn't see this. So there may even be some physical interpretation for those arrows which are not of this form, but I really don't know. I would like to have the characterization which singles out the one is coming from. But this is very much going already in the direction of reconstruction of the algebra. It doesn't reconstruct the multiplication of these guys, but it reconstructs at least the elements in the algebra from this. And the key, I think, will be to look at this object more closely, which is one of the projects for the near future. And as I said, this is a domain, and there's a rich theory in domains. Basically, are pose sets which have a lot of structure, which allow you to talk about approximation in a suitable way, and it should just become. Well, this will have a much richer structure than we looked at so far, and this will give new conditions on arrows. We just can classify arrows according to these extra structures we have here. Okay, so quantum states, of course, are what assigns values to physical quantities, if you like. At least in classical physics that's the case, and we will see eventually can use this also here. And they assign truth values to propositions. That was for a long time the primary perspective in the Topos approach to talk about the logical aspect of things. Now, if I want to talk about arbitrary quantum states, you know that there are basically two levels. One level is I can take pure states, and that is what we saw before, that for pure states you get a representation by these pseudo-states, and then every proposition has a truth value given by the internal logic of the Topos. In ordinary quantum theory you would calculate expectation values for projection operators, so you would get a real number between 0 and 1, interpreted as a certain probability that upon measurement this proposition will turn out to be true. So your measurement will give you a proposition is A is in delta, again with this symbolic notation, then the probability in a given state psi on the quantum theory for this proposition to be true is just the expectation value of the corresponding projection operator, and it means if I perform a measurement of A in the system in the state psi, and with this probability a measurement result will lie in delta. And this we already replaced conceptually by these internal truth values, which don't have to refer to measurements. There's a question or not? Okay. And the second level that comes in is when I talk about more general quantum states. Most of them will be of the form that they are convex combinations of vector states, so density matrices. And this introduces another level of probability, which is very close to a classical lack of knowledge interpretation probability. Because if I have, let's say, C times psi 1 plus 1 minus C times psi 2, and physicists would say, okay, this is a quantum state where I do not really know which one of psi 2 and psi 2 I have, the probability C, I have this one, probability 1 minus C, I have this one. So, the point I want to make here is that when we talk about outrage states, we should not expect to get just truth values. There will be real numbers coming into this game just from the fact that we have these convex combinations. So this will not be treated entirely in logical terms within the topos. There will be real numbers coming into this in a suitable sense.
They should be kept raw, shouldn't they?
Oh yes, okay, of course I should write yes. Because yes, of course, it's not the vector sum, it's actually the sum of these matrices if you like, and it's if psi 1 and psi 2 are orthogonal, then this basis, this matrix becomes C 1 minus C, of course. So it's the corresponding density matrix. Yes, that's actually important. I must have it in this Kent-Brunner form, otherwise I would take the vector sum and this wouldn't be the right thing here. It would be another pure state, but that's not what I want to talk about. Okay. As I said, I actually want a formalism which is even more general than this. So there are states of phenomena which are not of this form, but it only happens in infinite dimensions. We basically talked about this in the first few lectures on the function analytic aspects, but just to remind you of some of the basic facts, I'll briefly say what a state of phenomena is. So N is a and state. I will write the state itself as rho, while physicists often write the density matrix as rho. If I actually want to talk about the density matrix, I write rho tilde, something like this. So a state is a positive linear functional of norm 1. So it takes positive operators to positive numbers and takes the identity to 1. And it's easy to see that Southern-Jones operators go to real numbers. So, if I have rho 1 and rho 2 states in this sense, then I can form convex combination C times rho 1 plus C times rho 2 is also a state. So the states form a convex set. And this is called this convex set is called the state space. Convex set states. This is S of N. There is a certain danger in using this word here because state space is a word I've used in other connections already. This is the state space of the phenomenon, and so this is how I want to use this. I now want to relate this thing to our spectral presheaf in a certain way, and I'm thinking about the following. I want to compare this with the classical situation. So what is a classical state? classical state. So a classical state can either be seen as an integral on the linear algebra of physical quantities, and we have seen before that this algebra is an algebra of real valued functions on this picture here. State space of a classical system on P real numbers, and we have this picture. So these functions of this form, they form an algebra. Of course you take measurable functions, continuous or smooth, depending on what application you have. For us, we take actually the biggest class, we just say measurable functions, and they form an abelian algebra, and the state is an integral on this. This is a much more general notion of state than we've talked about before, because up to now we said, okay, a point S here, this is a state. This is a very particular integral that would just evaluate every function at this point. But in general, a state may also come with a lack of knowledge. For example, think of statistical mechanics. We're not really interested in the point in this huge state space of 10 to the 23 particles. We're rather interested in certain generic properties. So you will describe the state rather by a probability measure on your state space. This may be for practical reasons, as in statistical mechanics. This may be for a lack of knowledge, because you don't really know which particular state this is. So the general notion of a classical state is a probability measure on the state space, so that's actually the second description. Measure on state space. And here state space, of course, has this different meaning. It's actually this space P, it's like P here. And there's a connection between these two descriptions, and that's theorem by Rees representation theorem. If your space is reasonably well behaved, then every probability measure will give an integral, and the other way around. So that's the link, and these are two descriptions that we have on the classical side. So now let's look at the quantum side, and there we have this description. Quantum state. What I say here, it's a positive linear function of norm 1 on a certain algebra. So it looks very much like this. It is an integral, actually. The difference being that it's a non-abelian algebra. So I want to write this as an integral on a non-abelian algebra N of physical quantities. But can also see it as a probability measure on something. That's basically the open question. And if you look into function analysis books, you will see statements like there is implicitly a measure, but the problem is that there's no space on which this measure could be defined. And I will show now, that's the main gist of today's talk, that the spectral presheaf can take the role of this space. The global subobject can take the role of measurable subsets. So every quantum state, in this very general sense, gives me a probability measure on the spectral presheaf, and much more nicely I can go back. I can define abstractly what such a probability measure is, and I can get back a unique quantum state from this. And here the link will prove to be Gleason's theorem. Actually, a generalized version, I'll write this down later on. This is a very powerful theorem that we're using here. It gives us a nice link and actually fills in this gap. defined so far. So we'll use both stuff from the function analytic part, but also from the part around spectrum ratios and the Topos related things. Okay, I should say that this notion is somewhat more general than the density matrix notation. That most people will know for column states. So I called one theorem here. I think I did this before, but it's useful to see this again. First, I want to define state rho. Always means for a fixed phenomenon, you might not always write this. State rho is called normal if following holds for every, and I'll put countable in brackets, say something is in second, every countable family projections. For example, think of an orthonormal basis, and projections onto the basis vectors will give you such a family. If for every such family we have that rho evaluated showing I is, well, the join actually is the sum, because then pi was orthogonal. The sum over I rho. So this is a certain kind of continuity condition. That's how you should read it. And normal states have all kinds of good properties, as you may even take from the names. It's a good tradition in mathematics to call the stuff that's nice and easy with positive words and stuff that's not so easy. Negative words. So normal states are a good thing, and the theorem is every normal state has a decomposition as a convex sum of vector states. So every normal state rho is a convex combination of vector states W, sorry, I, N, and we can even pick these vectors here pairwise orthogonal. So rho is sum over I is from 1 to dimension of H, but this also holds for infinite dimensional spaces of I, and the sum over I of these coefficients AI is 1. So that's the convex combination. Didn't say yet anything about this countable here. In physics, you very often assume that your Hilbert space is separable, which means it has a countable basis. Everything I proved today actually would work also for the non-separable case, but since the usual restriction in physics, we can assume that our Hilbert space is separable, so it has a countable basis. Then, of course, defining a normal state just requires that for countable families this holds, because there are no uncountable families of directions. So this is for space H. Okay. And then this is just generalization to outer dimension of density matrices. Because if I write down this W psi I in the form of W psi I is the same as this W psi I. This thought of as a matrix, now let's think in a finite dimensional situation, would be a matrix of this form. It's a diagonal matrix. They have lots of zeros, they have a single one, the rest again is zeros, off diagonal it's all zero, and this here is the position I. So writing down this thing as a matrix gives you A1, A2, all these AIs on the diagonal, and that's it, that's your density matrix for you. There is another theorem, it's like this here. So it's the following, let's relate to what we did now. A normal state is of the form rho goes from N to C, of course, and takes A into trace rho tilde A for a positive trace class operator rho tilde of trace 1, and of course rho tilde is the density matrix, at least if you have a finite dimensional situation, you can really think of this as a matrix. Okay. This exactly this distinction. So I call the state itself rho. Physicists often call density matrix the state. So distinction by this tilde. But there's nothing much happening here. In infinite dimensions, of course, all the stuff with the trace becomes more difficult. But even for matrix algebras, if you have intuitively infinite matrices, you will not have that every operator has a finite trace.
Identity.
So there are trace class operators, those are which actually have a finite trace. And trace class operators form an ideal among all operators. So if rho tilde is trace class, then also this product A will be trace class. So this is well defined. This is a usual thing how we calculate expectation values in quantum theory. So in quantum theory, we mostly concentrate on normal states. But there are certain situations where you want to consider non-normal states. There's sort of KMS states, which come from thermodynamics, and if you look at stuff that Kohn is doing, and this has good physical interpretation. It's pretty complicated, but there are non-normal states which do play a role also in physical applications. So I want a formalism which is entirely general, and I want to signal later on the normal operators in the formulation.
Is this Gleason's theorem here? Quite similar to it?
No, Gleason's theorem is not here. At which point? This one?
No, I mean in the bottom right.
This one. Oh. No, this is a consequence of this one, actually. Well, okay, you could say the fact that we do. Let me think for a second. It's a question. Well, this is not Gleason's theorem. Gleason's theorem is weaker because we do not start from a state. We actually start from something which is called the probability measure on projection. So we'll define this later on.
Yeah.
It's not too far in spirit from Gleason's theorem, but you start from something stronger, so this is easier to prove. In particular, we know that rho behaves linear on the whole of n, while in Gleason's theorem we just have additivity. Wieser's theorem works for us in its proof. And this was my initial thought actually. Wieser's theorem just get something which is linear from conditions only on commuting parts of the whole story. And of course the spectral presheaf is cutting up the whole thing into commuting parts. But Wieser's theorem then is strong enough to reconstruct the state on the full algebra, so get back linearity also non-commuting parts. And that's where this theorem works for us. And this is also why the spectral presheaf is not too commutative to do this. Okay. Yeah, so I don't want to say much on ordinary measure theory, but of course the idea is very much you have some kind of set, you have distinguished family of subsets, and then you have a mapping from these subsets to positive real numbers. For us we have probability measures, so you map to numbers between 0 and 1, and you assign a number to each of these subsets, these measurable subsets, and there are certain conditions in particular. This should behave additively on disjoint subsets. That's the main thing. So we get the idea, if we want to generalize this to our situation here, we should first of all have distinguished family of sub-objects of the spectral presheaf, which take the role of measurable sets. And we should have an analog of this. Well, first of all, we should have the probability measures of the whole spectral presheaf should be of measure 1 in a suitable sense. And we should have an analog of this property, disjoint subsets. The measure behaves additively on these. When you think about a bit like how do these sub-objects of sigma look like, you will find it's pretty hard to define disjoint stuff. Well, you can do it, of course, but then the Heiting algebra aspect comes into the game, so taking two disjoint sub-objects together will not give you the full thing. There's exactly the law of excluded middle failing there. So we will actually look at the closely related property, which is in ordinary set-based measure theory the following. If you have two sets, let's say S1 and S2, what's the measure of the union? Well, let's say mu is the measure, mu of S1 union S2. Well, this should be something like the measure of S1 plus the measure of S2. But then I'm counting something double, then exactly the overlap is counted twice. So I should subtract mu of S1 intersection S2. And here it doesn't matter whether they overlap, so rewriting this very slightly, you get mu of S1 plus mu of S2 is mu of S1 union S2 plus mu of S1 section S2. You know a bit more of measure theory, you will actually know that if you want to call something a measure, there will be some regularity conditions. So how does it behave on infinite collections, and some kind of continuity conditions, basically. We will see, not surprisingly, that normal states will give us regular measures in a certain sense. But since I won't be entirely general, I will not require anything more than this condition on finite relation. So this is very, very weak. We'll see this. Okay, let's wipe this out. The first thing I want to do is I want to take a quantum state and define such a probability measure. So let row state of n define. The first thing I have to decide is, I already said this, what are my measurable subsets? Now the whole of von Neumann algebra theory, especially the theory of states of von Neumann algebras, is sometimes seen as non-commutative measure theory. That's precisely because we have this idea there is an integral of a non-commutative algebra, And implicitly there's a measure going on. So, and what's special about phenomenologists is that they have lots of projections, and so it's at least it's a natural idea to look at these subobjects that we had in another connection already, namely those where each component is the cloak and subset, so each component corresponds to a projection. These are our famous cloak and subobjects. And this is why our measure will have as its domain cloak and subobjects. Those are the measurable ones. And I mentioned this, I didn't prove it in detail, but you can show quite easily that this is a complete Heyting algebra. So it's the analog of the sigma algebra of Borel subsets for the Lebesgue measure. This would be these guys. So mu rho, I think this is where we're going, let me use another pen. Mu rho goes from the cloak and subobjects of sigma. Okay, the next question is, what is the codomain? In ordinary measure theory, you would just assign some real number between 0 and 1 to the subset. But these guys, they are not just sets. They are rather pre-sheaves, so you have one set for every v. And this is exactly why for every v we get one real number between 0 and 1. Of course, there are certain conditions. I write it, since it's an Topos external argument anyway, I write it externally. I'll explain in a second what this means. This is, and how do I want to do this? It's very, very straightforward. S, which means I have this, I have a subobject, so this has all these components, SV. This goes over to, well, just my state rho, evaluated on where this SP, SV, and we have that SV is a subset of sigma v, and we had this lattice isomorphism, this is actually Cloten by assumption, lattice isomorphism alpha from projections to the Cloten subsets of sigma v. So if we start from SV, then P SV is the functory alpha t minus 1 SV, but that's a bit clumsy, so I rather want to write PSV. So this is again this trick, we can go back and forth between Cloten subsets of the Gelfand spectrum and projections in V. So, and I'll do this for all the, and that's the whole definition. It's very, very simple. What's happening here? I take my subobject S, I look for each V at the component SV. This corresponds to a particular projection in V. I just let my state rho act on this. So it's nothing but the expectation value of this projection in the state rho. And this is a number between 0 and 1. And there is a certain condition coming from the fact that this is a subobject. We saw early on that the easiest way is S is, well, S is a subobject, subobject actually, and we have that primes contained in V. Then it follows that P S V is smaller or equal to P S V prime. This was the condition for being a subobject. This implies here that if I go from V to V prime to a small algebra, my projection will get bigger. So also rho of this can only get bigger. So I can see this as a function from V of n to the unit interval, which reverses the order. I go to smaller algebras, I get larger numbers. And this is for antitone, so order reversal. You can also see this as global elements of a certain prechief. That's how it's in the paper. Should have given a reference. I'll give a reference later. This paper, all this stuff is done. But arguably, this is a very simple definition. You directly evaluate your state on all the components of your global subobject. You get a bunch of real numbers. The only thing that's slightly unusual is that the measure of some subobject is not a single real number, it's rather such a collection under this condition. Smaller numbers V are assigned larger numbers. Okay. Some things are immediate. So we have that, actually I should say this. First is almost for all states rho, we have a at u rho of, let's say, the empty subobject. I don't know how to write it, I could write it this way maybe. It's a prechief, but it's actually empty. Well, what does this mean? The corresponding projection is always the zero projection. So rho evaluated in the zero projection is 0. So this gives me the number 0 for every v. I write this as 0 vn, just indicating a pulse for every v. And similarly, let's leave this here for a second, u rho of the whole of sigma, which is the biggest element in this Heiting algebra, is the function that's constantly 1 on the Fn. Why is that? Because every component is a full Gelfand spectrum. The corresponding projection is always the identity. This is a state, so rho of the identity is 1. Okay, this is justifying that. We haven't justified that this is a measure actually, but this, if we see later on this is a measure, then this will be a probability measure where the full link goes to 1. And the other thing is a very small proof, basically just using the definition. We wanted to show that this condition here holds analogously. And this again holds for all rho and for all S1, S2 in sub CL sigma we have, so this is, well, it's very easy, but I still think I should use my notes for this. Well, I'll start writing here, probably need a bit more space. So, mu rho of S1 or S2. Okay, and something interesting is happening here. I should say this. I should say before I do this calculation, one thing is very important in this definition. It's entirely local, so the number that I assign at V only depends on the component of the subject at V. So it doesn't take anything else into account. The only condition I get is what I said here. These numbers are not arbitrary because the components have a certain relation to each other because it's a subobject. That's the only condition between different V's comes from this fact that we have a subobject. Okay, and this is why I can. Okay, another thing is the lattice operation. We looked at the lattice operations here in this Heiting algebra. They're also local. They're also for every V independently, so stage by stage. This is why it makes sense to write down something like this of V. And if I can prove something for all V, then I have proven it globally. Okay, plus mu rho of S1 and S2 V. So just use the definition. What's this?
That'll probably be a telemarketer.
Hello? sounded something.
Yeah, the thing is, there's a robot that rings all the numbers one by one.
Yeah, it was of course automatically just taped a message. Okay. The funny thing is you can't do anything about it. I mean, you can shout at it. It won't help. Yeah. Okay. So I'll just write down the definition. Well, this is also going. It's not very good. So if it becomes hard to read, please tell me. So this is P S1 at V, or P S2 at V, plus mu rho of, no sorry, here I already rho of P S1 V and P S2 V. Okay, the first thing I use is linearity of rho. So I get rho of S1 V or S2 V plus P S1 V, sorry, V and P S2 V. Okay. The next thing, this is just one of the, we have to observe that all these are projections in V, so they all commute with each other. And there is a rule which basically is exactly saying this, because I can actually think of these as closed subsets if I like. So I can write this as rho of P S1 V plus P S2 V. Okay, then linearity again. This is rho of P S1 V plus rho of P S2 P. Then finally, using the definition, again, this is mu rho of S1 at V plus mu rho of S2 at V. Okay. The thing is that you can see here, I said at this point we're just using linearity of rho. This happens here and here again. Of course, every quantum state rho is linear. Normality would mean it behaves linearly also on infinite corrections in a suitable sense. Don't have to require this just for this example, which of course just refers to two sub-objects. Taking these two things together, I think it's justified calling this thing a measure, at least in a very weak sense. Regularities is another business. Okay. One observation is that you have to think about a bit how the high-dimensional structure here is, but you will get, if you take an arbitrary non-empty subobject S, so this is basically the lemma. I don't want to go through this, but so S sub CL sigma S non-empty, then we actually have S or not S in the height negation, something which is properly smaller than, oh sorry, I should write more, I should write sigma, which is the top element in there. And of course this also implies that mu of S or not S is smaller than this function, which is constantly 1. So complements are not proper complements, they're just pseudo-complements, and you can see this in the measure also. So if you know what the measure of some cloak and subobject is, it's not just possible to say, okay, the measure of the pseudo-complement is 1 minus this guy. It's just not true.
If you have S or not S, would that give you 1?
Not S. You
Sorry,
mean,
not S. Not S.
Not S.
Or not
Or
S.
not S. It should actually. It's a good question. I think this gives possibly 1 yes. Okay, I think it's, well, I put a very small question mark here. I think it's true. Okay. In this way, from every quantum state we get such a measure. That's something. And the second step would be to say, okay, can I say abstractly what such a measure is? What kind of conditions do I need to say this comes from a quantum state? And when I first wrote this down, well, I didn't have much hope that I could reconstruct quantum states. So I said, following define probability measure on sigma, or more precisely on some objects, as a mapping mu from sub sigma. This is not really officially drawn. That seems good. I'll write this again. So mu goes from sub sigma to and some functions S goes to mu of S. Okay, let's write this. Let's write it this way to make it really explicit. One thing. I wanted also this definition to have something local. So whatever I assign at V should just depend on the component of S at V. But of course I need some conditions. So the first is mu of sigma is supposed to be Vn. And the second is just this thing. For S1, S2 we have that mu of S1 plus mu of S2 is mu of S1 or S2 plus mu of S1 and S2. Okay. So this would be very close to this, and just forget about the fact that there's a quantum state involved. I want to emphasize again that everything in this definition is very, very local. So this component at V just depends on SV. This addition should have said this more clearly. These are, by adding two such order reversing functions, this is also component-wise. It's easy to see you get another of these functions. Usually the values will of course not lie between 0 and 1 anymore. They will lie between 0 and 2. But that's not a problem for this condition. And so this is locally at each V. This join and this meter also locally at each V. And again this sum. So everything is very, very local. And the only relation between different contexts comes from the fact that this is a sub-object, so I will still get these order reversing functions. Okay, when I wrote this down, it's kind of what I canonically get over there, but it looks too weak to reconstruct a unique state. let's look at Gleason's theorem in the form that I will need here. Again, there is a certain overloading of notions. There will be, we'll talk about probability measures on projection lattices now, which is different from probability measures on global sub-objects, but there's no better way of doing this as a traditional way that is used in mathematics. So, well, let M from the projections in some phenomenon to the unit interval be mapping such that a M of the identity is 1 and B if P Q equals Q P equals 0, which just means the projection P and Q project onto orthogonal subspaces. Then M of P plus Q, which actually is nothing happening here, is M of P or Q, because they are, in this case, these operations coincide. Quantum follows here, so it's M of P plus M of Q. So it behaves additively on disjoint things, that's very much the idea. And disjoint is expressed here in the fact that they project onto orthogonal subspaces. So if I have such an M, this is called the probability measure on projections. Trivial that from this binary additivity, finite additivity follows, but I don't require countable additivity or something. So an M is called a finitely additive probability measure on P M. So I think I'll write down Gleason's theorem and we'll take a break. This is a generalized version of Gleason's theorem. Gleason's theorem originally is from 1957. It's an extremely interesting proof. For him, N was all bounded operators on the Hilbert space, and he actually requires not just the finite additivity, he requires countable additivity. What has been generalized, so the theorem is if M to 1 is a finitely additive probability measure, then there exists a unique state of N such that, well, let's call the state rho, or rho M, and such that for all P and P M, we have that rho M. P, of course, is just N of P. There is one small extra condition. I cannot do this for an arbitrary phenomenon algebra, but I can do it with this one by 2 matrix algebras. This is not restricted, so Gleason's theorem also starts typically if your Hilbert space is 3-dimensional, which would exclude also 2 by 2 matrix algebras. The problem is not that you couldn't find a mapping of this kind, but it would not be a continuous linear functional, which the state is. So, provided that, that's the Bosch way of saying this, the 2 by 2 matrix size excluded, provided that M has no direct summand of type 1, 2. So this is from the classification theory of phenomenon algebras in type 1, 2 are exactly 2 by 2 matrix algebras. And this is more general than just complex matrices. You could have 2 by 2 matrices where the entries come from an abelian phenomenon algebra. So this is why I don't just say there's no M2C. So, okay, that's the theme. Let's take a break here. Okay, so now let's prove that from mu this form you get back a unique quantum state. What do? There's one canonical thing to suggest. Define M of P to be, I'll just write it down, mu S V, where of course I pick a subobject as such that this projection is P. I have to show that this is well defined. That's the main task. So I could pick another subobject, I could pick another subvariable V, and I have to show that this is well defined, so I always get the same number. Then I have to show that this gives me a finitely additive probability measure. Then I can use Gleason's theorem to get my state. So first of all, does my mu give me the same number whenever this component is the same? So to show mu of S V is mu of S tilde V tilde if P S V is P S tilde V tilde. Okay, and there's no obvious reason why this should be the case. All we have are these two conditions, so maybe I will keep this for reference. And why not? First thing is I prove a lemma for a kind. In the first step I keep my subobject fixed, so I do not have two subobjects in the game, I have one subobject. So sigma such that for some pair V prime and V such that V prime is a subintegral of V, projection S corresponding to SB is the same as the projection at V prime. Then we have that U of S V is mu of S V prime. Okay. How do I see this? Let's see. Okay. First of all, just to show you that this is always possible, I can always find a subobject with this property. So just especially on e.g. delta P S V as this property. Prime is the same thing. So I can always find some object which has the property that I assume. Take another subobject, another subobject S prime, such that S prime V, sorry, that's right in terms of projections, P S prime V is the same as P S prime V prime, and this is 1 minus P S V, or S V prime is the same thing. And you can also find one guy with this form, just take delta 1 P S V. So this also always exists. Okay. Then we have S minimum S prime at V. Well, this is 0 V, which is just empty set. I'm now thinking in terms of total sums. In terms of projections, it's the product between 1 minus PSV and PSV, which obviously is 0. We also have that same holds at S V prime, and the joints of both of them give me sigma V respectively, sigma V prime. So it's like this down, S join S V is sigma V, and S join S prime, and V prime is sigma V prime. Okay. Now, mu of sigma V is 1, is also the same as mu of S or S prime. I should write this way, one more bracket. Now I use this rule 2 here, to do something about this expression. So this is mu of SV plus mu of S prime V plus mu of S minimum S prime V. And this guy is 0 from what we saw, so it is this sum. This goes. this, taken together, implies that mu of S d prime must be equal to mu of SV. And likewise, if you want to write this down, mu of S prime d prime is equal to mu of S prime d. This is 1 minus mu of S d. Okay, it's very simple. One nice thing about this is that I was arguing here with projections, but the argument actually doesn't need this going back to projections. What I need is a subobject, given some S, I need a subobject S prime, such that these conditions these conditions must hold. Okay. Okay, so this proves the lemma that for a fixed subobject SV, if these components coincide in the sense that they correspond to the same projection, you must assign the same number to them. Okay. I proved another lemma, and we're almost there actually. Since the time is good. S and S tilde is Kelvin subobjects such that for some V we have P SV equals P S tilde V. So what we do here, we have two subobjects but we keep V fixed. Then we get that mu of SV is equal to mu of S to V. Okay. How do we prove this? Mu of SV plus mu of S tilde V is equal to, well, using this rule is mu of S or S tilde at V plus mu of S mu S tilde V. This equals, let's see, what am I doing here? Yes, okay. This mu of S V. So actually using how is the meet defined, at least actually the union of these sets. So it's this union plus here we have intersection mu of S intersection S to V, and now by assumption these subsets are equal because they are subset of the same Gaussian spectrum corresponding to the same projection. So this is what I can use here. So both this union is just SV, and also this intersection is SV. So I get mu of SV that's it. So I see that this sum, because this sum, and I'm done. Okay. Again, at this point, well, actually I do not have to talk about projections at all to prove this. I'm emphasizing this because it's nicer to make the argument without having to go back to projections. It's nice that we can directly argue on the level of sub-objects. We have to go to their components, which is, well, if you really think in Topos terms, the thing is the whole sub-object, so you shouldn't talk about the components, but we're not dogmatic at all. We want to prove something in a nice, straightforward way. Okay, now we have these two lemmas, so you can either keep your sub-object fixed and look at different contexts and get the same value from rho, or you can take two sub-objects, keep your context fixed, and at the same number, and combine the two things to show that we can vary both. That's done the following way. Just write down again the assumptions that we have. Let S be a sub-object such that P SV equals P for some projection P that I fix, because I want to assign something to P. So I find a sub-object which has at V this component. And let S tilde be another subobject such that P S tilde B tilde, so I vary both the subobject and context, and of course they both must equal P. Then rho of SV equals, no, I should write no, sorry. I should write mu of SV equals mu of S tilde B tilde. So this should actually form this proposition maybe. And proof is the following. Okay. The first thing is mu S V is equal to mu of delta of P V. This is by lemma 1. Let's call this lemma 1. So this is lemma 1. These are two different sub-objects. No, sorry. No, this is actually lemma 2. These are two different sub-objects, but they have the same component at V. So this is lemma 2. Then this equals mu of delta P V, oh sorry, yes, V prime, and I don't want to write V prime, I want to write V intersection V tilde, yeah. Why is that? Well, both V and V tilde must contain P. That's what we assume here. This means the intersection also contains P. This is the smallest projection in the intersection, which is larger or equal to P, so this must be P itself. This means the component of this sub-object, well, now I have the same sub-object, but I have two different contexts, namely V and V intersection V tilde. So by lemma 1, now this is why I use lemma 1, those guys are equal. Then I use tilde. So I get some statement at B tilde. Then I use lemma 2 again to get mu of S tilde B tilde. So this shows our probability measure M, just given by picking something is well defined. And I think time doesn't allow this. It's very easy to see that you get something which is finitely additive. This is extremely straightforward from the fact that, well, how do we see this actually? Well, you see it from this condition locally. You just pick two subsets and this locally becomes 0, and then you get your additivity. To get a finitely additive probability measure on the projections of your phenomenon algebra, you use Gleason's theorem, you get a unique state. You can do this as long as you don't have a type 1-2 summed in there. And yeah. The trick really is to shift everything into these particular sub-objects in form delta p. We cannot control the behavior of S and S tilde on V intersection V tilde. They could vary. Nobody says that S tilde on V intersection V tilde equals this thing, and likewise S and V intersection V tilde doesn't have to equal this thing. That's not what we require. We just do one comparison in the same context, then some object which stays constant between different contexts, and use this downwards and then upwards to the other context, and then use again L2. Okay, so this implies the nice theorem that right here. I mean, it's elementary arithmetic, I know, but still I was surprised that it works out, and that you can get into a position to apply this theorem by Gleason. So the theorem we get here is every probability measure on sub CL sigma corresponds to a unique state row in state space of N. And of course, the first thing we did, from every such state we constructed a probability measure, so we can go back and forth. So I can just write vice versa. Of course, all the structures I have for SFN, it's a convex set, and it's closed, and it's suitable topology. All these things can be transferred to the space of these probability measures. And again, we have to include this, provided N has no type 1-2 summer. Maybe we should have said this more nicely. So it's adjective correspondence between states and probability measures. And how do we characterize normal states? The last thing I want to say. This is actually a nicer thing than what's in the paper. So write this here. Rho mu induces a normal state. This is a normal state. If and only if for all, again here you may have countable families, or if you have a separate Hilbert space, otherwise you require, that's for arbitrary families, for all countable families of stage by stage, you take the infimum, the supremum stage by stage. So stage. So you can of course read this as a regularity condition on the function. And this is quite nice that we can characterize the normal states in this way, because for normal algebraic terms, normal states are important. They are examples of normal linear functionals, so general linear functional. Basically, you don't have requirements of positivity and normalization. But the normal linear functions on the phenomenon algebra, they form Banach space, and that's a so-called pre-dual of your phenomenon algebra, and this basically fixes your phenomenon algebra. It fixes it as a Banach space, and that's very useful in many applications. So it should be possible to extend this from states to arbitrary normal linear functionals, and then we have a good notion of the pre-dual of a phenomenon algebra in these terms. And there are many other things that can be done with this result. In particular, Khan will look at some aspects of that in TFIL, and the idea is, if every quantum state is now such a measure, how can I see entanglement? How can I see these features that are so important in quantum information, and many other possible questions you can ask at this point. But there are already some preliminary results. Basically goes in the direction, if you have a product measure, it corresponds to a non-entangled state. If you have a non-product measure, it corresponds to an entangled state. So obviously you need two components here, and because you always talk about joint states of systems if you're talking about entanglement. So it's actually filling this gap in this diagram I showed, and it's a new way of thinking about